Hello everyone. Welcome back to the DSA for Beginner series. So far, we have learned arrays, stacks, queues, linked list. So all of them are linear data structures. So if you can see in the you know the the classification of the data structures, right? So under the linear data structures, we have arrays, linked list, queues, and stacks, which we have already learned. If you have not already watched my videos, please go ahead and watch my previous videos. So from today, we are going to learn about nonlinear data structures. We'll start with the trees. So where are trees used? So they are used in most of the file systems, databases, search engines, compilers, operating systems, most of the artificial intelligence. So in fact, many advanced data structures like binary search tree, heaps, tries, segment trees, B trees are all based on tree concept. So before solving tree problems, we must understand the fundamentals. So let's begin. Why do we need trees? So let's imagine a company structures where we have a CEO. Under CEO, we have engineering manager. Under engineering manager, we have HR manager. So under engineering manager, we have developer one, developer two. So can we represent all this in array? So it can be done, but I don't think it will be very easy task to do that. Can we do it in linked list? Maybe if you have a double linked list, but yeah, again it will be a tedious task. So this is where tree plays a important role in representing a hierarchical relationships. So what is a tree? A tree is a non-linear data structure consisting of nodes connected by edges. Unlike linked list, where every node points to only one next node, a tree node can have multiple children. So let's see one example of a tree. So here, let's say we have something like this: A, B, C, G, H. So if you see, this is a typical example of a tree. So here, if you see, this is a root node of a tree. Okay, so these are the child nodes. So if you see, so whichever tree which is connected to root node, those are the child tree. A topmost node is called a root. That is what we were saying. So for every tree, right? So we will have only one root node, and rest of the nodes will be either parent node or a child node. So so this will become the child node, and this is a parent node of the child. Again, so this will become a root node. So let's say if C has something, so this is the parent of I, J, K, parent of I, and child of B. So what are leaf? So we have one more concept called leaf node or terminal nodes. So in our case, so the nodes which are at the end of the tree is called leaf node. So in our case, so we have J, K, D, F, H, and I. So all of them are terminal nodes. So we have learned root node, parent node, child node, leaf nodes. So next we have something called edge. A connection between two nodes is called an edge. So this is an edge. So this is again an edge. So any two nodes which are connected will have an edge. So if you see, how are we going to calculate number of edges is total edges is equal to number of nodes minus 1. So here we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So 11 edges we have. So sorry, 11 nodes we have. So total number of edges are 10. So we have something called siblings as well. So here, if you see J and K are sibling, which are sharing the same parent. So this is the same typical relationship in our household. So there is no much. Okay, so we have something called depth of a tree. So what is the depth of a tree? So okay, here let's say mm, in this node, right? So if you see A is at depth 0. This is depth 0. Then B is at depth 1. So basically depth is how far a node is from root. If you see, so A is the node, root node, so depth will be 0. B is one edge away from the root node. Again, so C will have depth 2 and likewise. Next, so next, what terminology? We have a height of a node. So how are we going to measure a height of a node? So let's take an example, height of a node. So let's take a simple tree here. And so height will be the longest path from the leaf node, basically A to B and B to D. So this is the height of a node. So in trees, we have something called skewness. So let's say uh, skewness. If a root of a node or if any node has only one child. So for example, let me take an example so that it will be very clear. A, B, C, and D. So here if you see, each node has only one child. So this is the left skewed. It means the tree goes only towards left side. So same goes with, let's say if the tree goes only on the right side, so that becomes a right skewed tree. Okay, so we have got a decent understanding of trees. So let's see our next concept, which is binary trees. So what are binary trees? Uh, so a tree is called a binary tree if each node has zero child, one child, or two children basically. So at max, a binary tree can have only two nodes, two children. So for example, A, B, C, D, E. So this is a binary tree. So here if you see, for any node, we have zero child, this is 0. So this has two childs. So again, this also has two child, two children. So so in our binary trees, we have two kinds of binary trees. One is full binary tree. So here, if you see, each and every node has maximum number of nodes, which is two. So all of the nodes has two children. So this is a full binary tree. So we have another concept called complete binary trees, where all the leaf nodes will be at a height of h or a h minus 1. That means, so if you see here, the height of a binary tree is 2. So the leaf nodes are present at the height 2 or h minus 1, which is at the height of 1. So this is a complete binary tree. Okay, so let's see how a tree can be represented in Java. So here, if you see, we can define a class called tree node, which takes the value of a node, which is value, and then the left pointer, which is pointing to the left node of the subtree, and the right pointer, which is pointing to the right node of the subtree. So how are we going to insert into a tree? So here, if we see, we are going to create a root. Then root dot left will have it as a new value 5, and then root dot right will have it as a. So how this tree will look like basically? So 10 is the root node. This is the root node. Then left we have 5. Then right we have 50. So this is how a tree can be represented. So let's see why trees are powerful. Suppose we store 1 million elements in a linked list. So searching requires traversing node by node. So the worst case scenario will be O of n. So that means a million elements we need to search if the element is at the end of the list. So this is where tree comes into picture, where the data is data is organized way more efficiently than the linked list. So basically, so we will see in our future tutorials like why how the data is arranged, and how the traversing is done for the data retrieval. Mm, so in our future tutorials, we'll see how we'll see how to calculate the maximum depth of the binary tree, and maybe we'll see a binary search tree. We have a lot of questions to solve also from the lead code. So what did we learn today? We learned about tree terminologies: root, parent, child, leaf, edge, sibling, and difference between depth and height. How is binary tree? How can we represent the binary tree in Java? So these concepts are the foundation for everything. In our next video, we'll see the traversal technique for trees. See you in next video. Happy coding. If you have not subscribed to our channel, please subscribe. Thank you.